So today we're talking about contrast. We'll skip the outline here. We have made so far tests for a single parameter like beta 3 equals 0 or beta 6 equals 7. Now we make tests for linear combinations of parameters such as beta 3 minus 2 beta 1 plus 3 beta 7 equals 8, something like that. In the example that we saw in the last lecture, we regressed the percent change in sales volume on comp sales and indicators of whether or not one of two promotions was applied. And we found that on average, promotion 1 increases percent sales by 8.4% relative to no promotion, and it's significant at this value when adjusting for the other X variables in the model. And for X2, for the second promotion, we found that there's no evidence that the promotion had different sales relative to no promotion, because it's not significant, right? What we don't really know is promotion 1 different from promotion 2? We might have an opinion, but the default, no promotion at all, corresponds to a coefficient 0, right? So we know that the coefficient 0 and 2.8 are not significantly different from one another. We know that 8.4 and 0 is significant. We don't know whether 8.4 and 2.8 are significant from one another. So we can formulate this by introducing a new statistic, the difference of the two betas. Theta equals beta 1 minus beta 2. To conduct the test, we now compute the variance for this difference. And the variance is the variance of the individual components minus, because there's a minus here, 2 times the covariance between the two components, where the covariance is defined as before. Now, we don't want to invert a matrix by hand, and so it's possible to get these matrices out of the programs. So here is the way how to do it in Stata. And you see the variances are on the diagonal and the covariances on the off diagonal. This is a lower triangular matrix because it is symmetric. The variance between beta 1 and beta 2, no, the covariance, is the same as the covariance between beta 2 and beta 1. So we can read off the values that we need, the variance for beta 1 plus the variance for beta 2 minus twice the covariance between them. We get a value, that's the variance. We take the square root to get the standard error. In R, we can do the same thing. We get the exact same variance covariance matrix. The rows are ordered differently. Well, the matrix is ordered differently because the intercept appears first, whereas in Stata it's last. Doesn't matter. So from the regression output, we have estimates for beta 1 and beta 2, and the difference turns out to be 5.59. The confidence interval for our new parameter theta is that value, the estimated value, plus minus the critical value based on the t-distribution and the standard error. We computed the standard error on the previous slide. The critical value on the of the t-distribution for a 95% confidence interval, so alpha equals 5%, at 26 degrees of freedom is 2.056. This makes sense. It's pretty close to 1.96. We know 1.96 is the critical value for the normal distribution. It's a little larger, but not much, because 26 is also relatively large. We know that the normal distribution is Well, pretty much it reaches the limit to the normal distribution at 30, 50, something like that. It gets close to the normal distribution very fast, converges. So here we get then the confidence interval that ranges from 0.6 to 10.5. Note it does not include 0. We could have gotten the same calculation much faster, so I'm just doing this here to verify. There is a command that says lin commons data, the difference of this, and then we get the exact same confidence interval here, and the exact same estimate for the coefficient, and the exact same everything. Yes, and it also gives us the exact probability here, 2.9%. So we have the 95% confidence interval. Because it does not contain 0, we know that we will reject the hypothesis that the two betas are equal. Right? So that means, for what we're interested in, it means that promotion 2 is better than promotion 1. Or is it just the other way around? Let's see. Promotion 1 is better than promotion 2, right? It has a larger coefficient. Okay, so it's just the other way around. And where was I? So, and if I was to write down a formal statement adjusted for competing sales, promotion 1 increases percent sales by 5.6 percentage points relative to promotion 2 at this p-value on average. So here's a clicker question for you. We have the variance covariance matrix for this data. We have the estimate, standard errors, and so forth. And the question is, do we learn anything from the variance covariance matrix? And about the estimated standard errors here. So I will leave you to answer this question and move on. Linear combinations are more common than you think because they arise naturally during prediction. So for simplicity, let's look at just the simple linear regression model with one x variable. If we want to predict at x equals 5, then the predicted value is beta hat 0, the intercept, plus 5 times beta 1 hat. And the variance here, the variance is basically the variance of a contrast. Well, it's a linear combination. So we have the variance of beta 0 plus squared 25 variance of beta 1 plus 2 times AB, so 2 times 1 times 5, 10 times the covariance between beta 0 and beta 1. So, which leads us to a clicker question for you. If we have this simple linear model with one x variable, what is the variance of the predicted value for x equals 2? You have 4 options here, and I will leave you to answer this. This is the end of this segment.